All right. So welcome everyone. It's my pleasure today to introduce Eric Laber. He's so he's from the Department of Statistics and actually a bunch of other departments at Duke. He's has pretty broad interests. He works on causal inference, some mathematical statistics, in particular asymptotic, some algorithms and optimization, reinforcement learning. Actually, so I really encourage you. After the talk to go and take a look at this the webpage of his lab. It's very entertaining, and there's lots of little demos and videos, including some like robots. He's interested in applications to precision medicine and sports analytics and robotics as well. So today he's going to talk about one of these, I guess, a combination of those two things that I just mentioned, except for asymptotics. He's going to talk about small size considerations for precision medicine. So Eric, please take it away.
All right, thanks. Yeah, thanks a lot for having me. It's always, bittersweet to do these things virtually. It's wish I was visiting. I guess though I can, wear pajamas or something, and I guess that's a pro. But hopefully in person at some point. So thanks for the nice introduction, and thanks to Sasha for inviting me. And this is drawn from a bunch of different work that people have done, and I won't go through all of it, but I will just point out that this is heavily based on the work of Eric Rose, who's a postdoc now at McGill. And so all the heavy lifting was done by him, and I just want to acknowledge that he deserves the credit here. I always have this introduction slide to precision medicine, and I think by now everybody has heard this, but just so we're kind of starting from the same place, the stated goal of precision medicine is to find the right treatment for the right patient at the right time, or the right treatment for the right patient at the right dose at the right time, and so on. Keeps expanding. But this is just based on this idea that we know the best possible clinical care requires tailoring the treatment to a person, right? And clinicians do that all the time. They understand your own preferences, or at least they try to, and your life situation, and make treatment recommendations accordingly. From our point of view, we're trying to mathematize this whole thing, right, and try to operationalize decision making, as a reinforcement learning problem or as a decision problem. And the idea is that if we do a good job of that, and we only give treatment if and when it's needed and it's going to be beneficial, then not only do we, make patient outcomes better, but we also reduce cost and patient burden. And so there's a lot of interest not only in sort of deciding the right treatment to optimize outcomes, but there's, organizations that are interested in tailoring preventative medicine, for example, to reduce health insurance costs and so on. So this is all formalized through what are called treatment regimes or treatment policies. And they're just a way of formalizing clinical decision-making as a sequence of decision rules or functions, one per every stage of intervention. And those don't have to be fixed. They can be driven by patient events. But in any case, each one is a map from whatever information you have at the time to a recommended treatment. And here we'll define, just for simplicity, an optimal regime as maximizing the mean of some utility function or some cumulative clinical outcome if you were to apply it to the population of interest. There are other notions that may try to be safer by taking a percentile or something, but we'll just focus on the mean. So what do these look like in practice? So this is an example in post-traumatic stress disorder among cancer. This is joint with Sophia Smith, who's also at Duke. And so here, there's two stages of treatment. The first stage, you can see it reads like a list. If your distress score is greater than 3, then you get something called the cancer distress score. And I won't get into the science of this because it's not really the focus. But if your distress score is high, you get this mobile intervention called the CDC. Otherwise, if your PTSD symptom score is high, greater than 20, you also get CDC. Otherwise, you get usual care. So that's the first rule. The second rule, which is assessed after a fixed time period in this case, it says if you're responding, and that's operationalized in terms of your symptoms, then you just continue whatever you're doing. So if it seems to be working, you just continue. Otherwise, if you started on CDC and you have a PTSD symptom change of more than 3, then you add mobile coaching or M-coaching. So this is all done over the phone. Otherwise, if you started on CDC and your distress score is now greater than 4, add FaceTime cognitive behavioral therapy. Otherwise, So these are the kind of rules that we want to construct from data. And one of the things that happens is that we go and we run a sequential multiple assignment randomized trial or an observational study, and we try to take that data and then construct one of these rules. And here's an example of, or this is the trial that corresponds to this patient population. So that was used to form that rule. Here, you can see that each R, it denotes randomization, and there's two stages of randomization. So at onset or at the trial, or at the beginning of the trial, patients are enrolled either the distress coach or standard care. So I called this CDC in the previous slide. And then they're assessed for response. And if they respond, they continue whatever they were doing. But if they didn't respond, then they get randomized a second time. So here you can see it's to mobile coaching or FaceTime CPT and so on. And so we want to take data like this and extract a rule like this, or estimate a rule like this that optimizes patient utility. Okay, so what's the challenge here? The challenge is that we often aren't powered to estimate a sequence of rules like that. And sort of the classic way this was developed, and this has a lot to do with just the history of getting these trials, these sequential trials sort of adapted in practice, is that sample sizes are typically based on some very simple primary comparison. So it might be compare the mean outcome under two non-overlapping treatment sequences. So it might be, when I say non-overlapping, I mean, they're disjoint groups of patients. So it might be give the distress coach and then mobile coaching if they don't respond. That's one. And a second might be standard of care and then FaceTime CBT if you don't respond, right? So those two trajectories have no patients overlapping. We can do a t-test and size the study that way, right? And this is a very clear objective in terms of constructing, power and sample size. And the test statistics are standard, and that's important, especially when you're talking about getting through a study section who wants to understand the analysis. It's not a very good statistical reason, but that's part of the historical reason that this is the almost exclusively what has been done for about, I don't know, let's say 15 years in terms of sizing these studies. And then estimation of a treatment regime is typically done as a secondary exploratory type analysis. So you run one of these trials, you do your primary comparison, which might be two fixed treatment sequences, and then you estimate a rule like the one I showed you, and then you try to analyze that rule to generate new clinical insights. And the reason this is not typically used to size a study is that it's a composite hypothesis, meaning that if your null is something about the optimal rule or the optimal regime, you don't have it, right? So it lives in some space of regimes. And so that makes it a very complicated problem. It's not clear what criteria should be used to do a power analysis. And the test statistics are non-standard. So they don't say have a normal distribution. They don't converge uniformly over the parameter space. And so it makes it a bit of a mess. It's not a t-statistic anymore. So what's done in practice is the following. You design your SMART and you run your primary analysis. So this is sequential multiple assignment randomized trial or some other kind of trial. You design your trial, you run it, you do your primary analyses. And then you go and you estimate a regime. I'll just call it pi hat for now. We'll talk about how to estimate pi hat in a minute. And then you might evaluate it using some kind of cross-validation, or maybe you just take a point estimate and see if it looks like it's better than standard of care. And if it looks promising, then you run a second trial. And in the second trial, you randomize to your estimated optimal rule or optimal regime pi hat, and you compare that to some control, which is maybe an active control or something simpler. And then you compare these two using, again, a simple hypothesis test, because this is an independent sample of patients now. So the comparison of pi hat to control is, again, simple. It's just a two-arm trial. Okay, so what's wrong with this, or what's a potential drawback? Well, on the one hand, it's sound in that we're kind of doing things sequentially and incrementally. We're not using the data twice. All the test statistics are simple. It's easy to sort of convince, let's say, a study section you can do all the comparisons you're claiming you can do, but it requires two distinct trials, right? So you had to run first this trial, get your data, and then run this follow-up confirmatory trial. So there's higher costs, there's delayed clinical impact. Anyone who's ever run a trial knows how long this takes. But another problem is that pi hat may be of low quality. So remember, you didn't size the trial to ensure you had a high quality estimator of an optimal treatment regime. You just sized it for some simple comparison. You estimated it after the fact. And so the consequence is that you might end up with poor patient outcomes. And the reason that happens is that, well, suppose that your estimated rule isn't very good, even though an optimal tailored treatment regime is good. So this might not look very good. We don't run the confirmatory trial. We miss out on tailoring. That's one option. It looks promising, but it's far from optimal. And so we run this trial and this trial fails. And then we don't adopt a personalized strategy. Or this looks good. We run our trial. It looks better than control. But we still have no idea how close pi hat is to the true optimal in this class. And so again, we may be leaving a lot on the table in terms of how we treat our patients. And so the ultimate result is that, potentially worse patient outcomes, but also we may obscure, critical factors sort of in pi hat or new clinical information that would be contained in a high quality personalized treatment strategy. And so in some ways, the ideal thing is to run a single trial that allows primary aims to be conducted or evaluated, and also to estimate and evaluate an optimal treatment regime. So we want to size the study so that we can estimate pi hat with a guarantee in terms of its precision and performance, and then also be able to do some kind of test regarding pi hat. So that's the goal. And I should have said this at the beginning, but please just interrupt me at any time if there are any questions. Okay, so why has this not been done before? Well, one reason is that the idea of estimating a personalized treatment strategy is very closely related to the identification of subgroups. And in fact, there's sort of this correspondence between, if the optimal rule recommends treatment one, then that is sort of the subgroup of people who will do better on treatment one than the alternative, right? And so, of course, that's associated with things like data snooping and a lack of reproducibility or generalizability, a lack of rigor. And this is a sort of a misconception, but it's widely believed in the sort of treatment regime, personalized medicine community that sizing a trial to estimate an optimal treatment regime with guaranteed precision would require an enormous sample size. And even if you could do it and you did have a big sample size, it would be very hard to guarantee frequentist operating characteristics because of this non-smoothness of the estimated rule. And so consequently, it'll be intractable, either because you need a big sample size or because you can't sort of provide performance guarantees without very strong and unrealistic assumptions. So that's sort of the background. And so the motivation for this work was in part just from working in this area for a long time and wondering whether or not this was really true, and eventually just deciding to kind of dig into it. And the other reason is that I've been involved in sort of dozens of these trials, and they all want to estimate one of these rules, and they want guarantees. And we sort of always had to say, well, we can't provide those for you, right? And so now we have trials in the field that do have these guarantees and have been sized for those. And we felt like that was worth doing. Okay, so the goal is to construct sample size procedures to ensure estimation and evaluation of an optimal treatment regime with performance guarantees. And so the way we're going to do it in this talk is we're going to look at two extremes. The first is we're going to sort of just put distributional assumptions on everything. So this is sort of the simplest possible case. So you just sort of assume everything has a nice parametric form, in which case we'll see that you get nice sort of test statistics, everything's asymptotically normal. But what's happening there is you're implicitly excluding all this non-standard behavior that's known to be a major problem in this area. So you put this structure that structure precludes any non-regular behavior, but you get nice closed form solutions. And then at the other extreme, we'll only assume moment and tail conditions. We want to assume the models are correctly specified. We want to assume any kind of smoothness. And then we'll have sort of a conservative confidence procedure. And the idea is that you can kind of fill in the middle. Okay, so here's an outline for the rest of the talk. First, I'll just review estimation of optimal treatment regimes. Then I'll talk about the sample size when you put a lot of structure in the problem. And then, what do we do if we don't want to make any assumptions other than, the moments we need to exist? And then I'll talk a bit about some simulation experiments that we ran and make some concluding remarks. So that's the idea. Okay. So we're going to talk about sort of the simplest case in which all these issues arise. This is also the most common trial design. It's a two-stage trial with binary treatments, although this extends to more complicated trials. But the idea is that after you run the trial, you're going to have N patients. And for every patient, you're going to have a trajectory X1, A1, X2, A2, Y. So X1 is baseline patient information. A1 is the first treatment that you assign them. X2 is the information you collect during the course of the first treatment. So this might be longitudinal information. A2 is the second treatment, again, coded -1, 1. And then Y is its utility that's observed at the end of the trial, and it's coded so that higher values are better. And then just to make the notation more compact, we'll define the history H1 equals X1 and H2 equals X1, A1, X2. So just H, T is the information you have at the time you're going to assign treatment T for T equals 1 and 2. And then a treatment regime in this context, pi is just a pair of functions pi1, pi2, where pi t maps, a history to a recommended treatment. So if you were following pi, then if a patient presents with history ht equals little ht, then they'd be assigned treatment pi t of ht. Okay. And the way that we're going to estimate an optimal rule is to use approximate dynamic programming. And so just a quick refresher. So the optimal regime we're going to define as maximizing the mean outcome if you assign treatments under pi. So I'll write that as v pi, which is the expectation under the distribution induced by assigning treatments under pi of y. And I'm sweeping all the kind of causal assumptions under the rug here. If you're interested, that's developed in detail in the paper, but I'll just sort of hand wave here and say this is the mean outcome if pi is used. And then we can characterize the optimal regime using the so-called Q functions. So Q2 of H2A2 is the expected outcome given second stage history H2, second stage treatment A2. And so this is the mean outcome for a patient with history H2 given treatment A2. And then Q1, H1A1 is the expectation of the maximized second stage Q function given first stage history and action. And we know from dynamic programming that pi t opt, the optimal rule at time t, is the argmax over AT of QT, HT, AT. And so this form immediately suggests the strategy for constructing an estimator. We can just estimate Q2 using a regression of Y on the history and action, and then our treatment. And then we can take our estimator of Q2, plug it in here, and regress that on H1 and A1, and then get an estimator of Q1. And then pi hat is the argmax of Q hat. So this is kind of the standard approach.
Hey, are you assuming a Markov structure here?
I'm not. So this is because it's only two stages. I'm not assuming it's Markov here. So the Q1 and Q2 could be different. Yep. Thanks. Okay. Now, if you go to like an mHealth type trial and you have an infinite or an indefinite horizon or a very long horizon, then basically all the same arguments I'm going to give apply, but you'll assume it's Markov and you'll have an estimating equation instead of this sort of just two regressions. Yeah. Thanks. Okay, so the starting point is that we're going to assume first that someone's interested in estimating the optimal rule using these Q functions, and we'll posit linear models here just for concreteness. So the algorithm is just basically plug-in estimates of those two equations I showed you. So we'll posit some kind of working models for the Q functions. Let's say QT, HT, AT indexed by some parameter vector beta t is HT0 transpose beta T0 plus AT HT1 transpose beta T1, where HT0 and HT1 are just features constructed from H. They could have basis functions or other transformations, but they're known. And so we just have a linear model. And we first estimate beta hat 2, so the second stage coefficients, by doing least squares. So here Pn is just an average over the data. It's the empirical expectation of y minus Q2 H2 A2 beta. So we do least squares, we get beta hat 2, and then to get beta hat 1, again, we do least squares, but as our response, we take the maximized estimated second stage Q function. So again, just do least squares to get beta hat 1, and the estimated optimal rule then pi hat t of HT would be the argmax of our estimated Q function. So that's QT, HT, AT, beta hat t. So it's the argmax for AT of this thing, right? So it's just two regressions, basically, or regression to maximization and regression. And so this is widely used for a number of reasons. It's just that if you have any special structure, you can just adjust your regression models accordingly, which is why it's popular in practice, but there are other you could take. Okay, so the criteria that we're going to ask for are going to be the following two things. And there's a whole bunch of tuning parameters or choices, but they'll be clear as I state the criteria, and they're pretty standard. So we want to choose a sample size n so the first criteria is related to power. There exists an alpha level test of the null that the marginal mean outcome under the true optimal rule is less than B0. So this is some measure of standard of care with power at least 1 minus gamma, provided that the true optimal is at least eta better than standard of care. So if there's a gap of at least eta between the optimal and standard of care, we want to be able to detect it with power 1 minus gamma. Yeah. So if it's worth tailoring treatment, we want to know with high probability that it is better if it's at least eta. So this is a clinically meaningful difference, let's say. And then we want this optimality property, which is the probability that V of pi hat is within epsilon of the true optimal in terms of its performance, with probability at least 1 minus zeta. So the first one is we want to be able to test whether or not it's worth tailoring treatment in a given context. The second one is we want to guarantee our estimated rule is within epsilon of the true optimal with probability 1 minus zeta. Right, so with high probability. Okay. Any questions on the criteria before we move on? Okay. All right, so the simplest possible thing you can do is just parameterize everything. And this is kind of the simplest vanilla linear model setup for these two-stage problems. And you start at the second stage and you posit a linear model. So we're going to assume that Q2 is in fact a linear model. So it's H20 transpose beta 20 star plus A2 H21 transpose beta 21 star. Okay, so the Q function is correctly specified at the second stage. And then you would like to have a linear model at the first stage, but it turns out it's almost impossible to have kind of consistent linear models at both stages unless saturated models. So the next best thing you can do is you can say, well, let's assume that the expectation of this first term, given first stage history in action, is linear in first stage history in action. Okay, so we have this linear model of this term. And then remember, we're taking the expectation of the maximization of this thing. So that'll be the expectation of this plus the maximization of this over A2, which will be the absolute value here. And so we're going to make a stronger assumption that this term here, H21 transpose beta star 21, is a linear model in H1, and it has some kind of additive error. Okay, so here I assumed it was normal. That's not critical. So say some tau star, that's the standard deviation times the standard normal. And so we have this sort of these linear models here. So it's not a linear model at the first stage because you're going to take an absolute value, you're going to maximize, but the components are linear. And finally, we're going to assume that these contrasts here, or these linear combinations here, 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 and here are jointly normal. Okay, so this would happen, for example, if the features were related to some kind of AR model. So this is the analog of a linear model in this two-stage problems. You basically make everything that you can linear and you make everything normal that you can. Okay? And so the idea is that this should be sort of the easiest case in which you get to the sample size. And you can really, like as I mentioned, you can relax and have any sort of nicely behaved error distribution here if you wanted, or any other kind of distribution here that's, again, nicely behaved. Okay. So
can you say a little more, like maybe in light of some example of how you decompose Q2, for example? You say it's linear, but then A2 is multiplying just the second part. I mean, like, can you give an example of what this means?
Oh yeah, sorry. Let me just good question. So here we've just had a contrast coding. So the idea is A2 is binary and it's -1, 1. So under treatment 1, or A2 equals 1, you'd have H20 beta 20 plus H21 transpose beta star 21. And then under treatment -1, you'd have H20 transpose beta star 20 minus this term. And so the idea is H21 transpose beta 21 represents the contrast between the two treatments. And that makes it easier to pick off the argmax as just the, whether or not this thing is positive or negative. And so these would be second stage features of the patient. And the idea is that these are the ones you think are important for choosing the optimal treatment. I'm not sure if I answered your question or not.
Okay. Yeah, so that's I was like wondering how you pick the features H0, H1, so that you know which ones to assign to this like A2 terms.
Yeah, so that's right. So the construction of H20 and H21 is sort of you can use kind of model building techniques that, but the challenge here, and I think this is what you're getting at, is that you have to do this before the trials run, right? And so when you're positing these models, often what we'll do is, we elicit kind of what variables are important from the clinicians, and we also look at historical data if it's available to try to get a sense for what those variables are going to be and which features are important. But one of the challenges of these sample size type things is you have to do it before you get any data from the actual trial itself. And so you have to posit a model, and typically you just err on the side of including more stuff in these features than you think you need to. And then you end up with a conservative bound, but it's better than the other way. Yeah. Sorry. Okay. So what I was saying is that there's this function G, and even though it looks kind of horrible, this just comes out of taking the expectation of the max of a normal, or the absolute value of a normal. So it's just a result of a normal integral. That's all this comes from. And that comes from looking, if you have this kind of structure here, where we're assuming that this term is in a linear model with a normal error. And then if I look at the expectation of the maximization of this thing, that'll end up being the max of, so this term has no A in it. Max of this over A will be an absolute value. And so that's where you get the expectation of an absolute value of a normal. And that's where you get this form. Okay. So then you can show that under sort of standard regularity conditions, in addition to the sort of linearity, just that moments exist, if we let psi denote a normal density, then the value of the optimal regime is a smooth function of parameters indexing that linear model. So in particular, there's tau star, there's omega, and capital omega, which if we go back here, you can see that's this variance term here, and the mean and covariance of this joint distribution. So it's a smooth function of those, and you can write it out as this sort of integral. And so the point here is because this is a nice smooth function of nice parameters, we can just estimate these, plug them in, and that'll give us an estimator of the optimal value. And then we can do all of our sort of usual sample size calculations just via that Taylor series. And so, more formally, if we make those assumptions, and v hat is the plug-in estimator of this, meaning I were to estimate these parameters here, just plug them into this function, then you can show that root n times that estimator minus the truth is going to converge to a normal with mean 0 and variance, say, sigma star or sigma star squared. And this itself is a smooth function of the generative model. And so this limiting distribution depends only on a single unknown scalar. And so this is like the ideal situation. This is what we do in a sort of standard testing problem. You might have, the mean minus the sample mean, is asymptotically normal. And then we can just invert that to get a sample size. And in particular, you can show that if we let sigma hat be a consistent estimator for sigma star, this variance, then a test that rejects when root n v hat minus standard of care divided by sigma hat is greater than a 1 minus alpha percentile of standard normal. This is in fact an alpha level test of the null we wanted, which is that tailoring is no better than standard care. And we can choose n as follows to satisfy the power condition. And for those who are familiar with sample size calculations, look familiar. This thing here is the variance divided by the clinically meaningful difference. So this is like the standardized effect size. This is the inverse CDF of a standard normal. That's the desired power. And that's the error of the test. So this looks just like what we see in Stat 101, right? And so just a simple, and it's not surprising because you just, we assumed everything was smooth. And so we should get something like this. But the caveat here is that this sigma star is not really meaningful clinically. It's not like the variance of your outcome under standard care or something like we would normally see. And so this is actually, it's a limiting variance of this thing, right? And so it's actually a very complicated functional degenerative distribution. And so in the paper, we have given upper bound on this. That's a function of like the variance under standard care that you can use in sizing the study. So even though it looks like it's exactly the same as sort of a Stat 101 problem, the form of this is not really clinically meaningful. And so it's harder to elicit. And so we show that that under minimal assumptions, it's bounded above by something you can get from clinicians pretty easily. Okay. And you can also show that, again, under pretty mild conditions, that the performance of the plug-in estimator pi hat, by estimating those parameters and plugging in, minus the optimal is bounded by some constant n to the minus delta v hat minus v opt plus a term that's little op of 1 over root n. And the point here is that we already know how to bound this thing, right? We know how to make this small. We just showed how to make this small. And so we can subsequently use our sample size that makes this small to then drive this down after this constant's known, and to drive this down to provide a performance guarantee. And so in particular, under those assumptions, you can show that this n is sufficient to satisfy the optimality criteria that pi hat will be close to pi in terms of its performance. And so in particular, it's phi inverse of 1 minus zeta. That's the probability that you want it to be near optimal times sigma star over epsilon squared. And so again, we get in closed form. And if you want them both to hold, you can take the max, for example, right? Okay. So again, very simple, depends on a single parameter. So just, to summarize this, obviously we got these very simple closed form expressions. We assume the linear mean model and normal error. It's not vacuous. You can construct generative models for which this holds. And you can check if the model was reasonable after you've run the trial. And it can be relaxed to kind of any smooth parametric model. But it also requires elicitation of this sort of sigma star or historical data to estimate it or to get an upper bound, which is not trivial. And it also, the structure is pretty substantial, right? You really are putting a lot of structure there. And so there's this sort of, we want to make sure that you can also do it without putting all the structure. And that's what I'm going to talk about next. Okay, so what do we do if we don't want to put all this structure there? And so Here, I'm just going to review kind of the estimator. So we're still going to use the same estimator, but we're not going to assume anything's right anymore, right? So the idea is you're going to get the data from the trial. You're going to run this estimator, but now we're not going to assume that it's correctly specified. So we'll assume that once you get the data, you do this regression-based Q-learning, where we posit our linear models for the Q functions, just like we did before. We do the two regressions. So beta hat, again, is argmin over beta 2 of our least squares criteria at the second stage. We also do least squares at the first stage using our maximized second stage Q function as the outcome. So we do two linear regressions, and then pi hat is going to be estimated as the argmax of our estimated Q function. So we have to commit to some kind of procedure. So we have to commit to analyzing the data in some way before we start the trial. And so this is how we claim we're going to estimate pi hat. And then when we talk about doing our tests and our asymptotics, because we're not going to assume these Q functions are correct, we still need to talk about some kind of limiting behavior. And so what we're going to do is we're going to define beta star t. So that would be beta 2t, beta 2 star and beta 1 star, to be what you would get if you replace these averages over the data, these PNs, with just the expectation with respect to the generative model. Okay. So we're not assuming these are the Q functions are correctly specified. These are just the projections of the Q function out of these linear spaces. And then we're going to define pi t Q opt of HT to be the argmax of QT, HT, AT, beta star T. So this is not the optimal, right? This is sort of what you would get with infinite data if you had committed to this strategy, right? And it's hard to expect to get better sort of performance given that you've committed to this method of estimation, right? So if it's specified, the best you could hope to do realistically is to just kind of, the limit of these estimators, right? Of course you can, yeah. So that's what we're going to talk about is convergence to this thing. Okay. So the idea is we'll impose less structure on the generative model. We'll only look at moment and tail conditions. We're not going to assume those Q functions are correct, as I mentioned. But it's important to note that both the power criteria and the optimality criteria are still meaningful in our misspecification, because I can still compare the performance of this thing to standard of care. I can still say, if I do this, is it going to be better than what we're doing now, right? So is it worth tailoring, given that this is how I'm going to estimate an optimal tailored strategy or optimal personalized strategy? Is that going to be better than standard of care? And we can still talk about how close the estimated rule is to the limit of that rule, even if we had an infinite amount of data, which makes sense if you're talking about power. So is n big enough so that we're not leaving a lot on the table? And if we were to go and get more data, we wouldn't improve much, right? So we wouldn't want a criteria, for example, that talked about being close to the true Q function, because the models aren't assumed to be correctly specified, right? So the big challenge here is that both beta 1 star and the value of the optimal rule as defined as Q, pi Q opt, are non-smooth functionals of the data generating model. And what that means is, or the consequence is, that there are no regular asymptotically unbiased estimators of these things. So no matter how clever you are constructing an estimator, you're always going to have a bias term on the order of 1 over root n. And standard normal approximations can perform extremely poorly. And the bootstrap or other kinds of approximations, if they're not adjusted, can perform quite poorly. And so our idea then is that we're going to base the sample size procedure on conservative inference procedures. So there's been work on how do we get, yeah.
Is the non-smoothness coming from the max?
That's exactly right. That's exactly
so
right.
Why don't you replace it with a softmax?
Oh yeah, so this is a great question. So you might think, or it's very natural to ask, like, well, why don't I just, instead of doing this, I just put something smoother here that's differentiable, say, right? So it turns out that this is a game you can't win, which is maybe surprising. So the idea is that if you smooth it out enough so that the finite sample behavior is like a smooth function, you end up getting this excess bias, and so that which ends up hurting you. And so you either have to sort of take that bias in the sense that the estimand now with the softmax in place of the max, that's like your new estimand, right? If we define the population analog, the difference between that estimand and the estimand you care about is either going to be really large, or it's going to be small, but then the finite sample properties are going to act just as if it was non-smooth. And so Susan across the river, my advisor, former advisor, Susan Murphy, worked on this with one of her students, Bibas Chakraborty, a while ago, and with this sort of shrinkage or trying to soften the max. And you can actually show that if you do that, you can end up being kind of infinitely worse in a mini-max sense from this inference point of view. Yeah.
I mean, you made like tons of modeling assumptions. You could just assume that what you care about is the solution to the softmax on the real problem, right? Which is somewhat justified by taking the max after adding some noise, for example.
Yep. That's the question is, do you want the estimand to be the softmax thing? You could say that's the estimand. That's the target for inference is the soft thing, right? But it turns out that can be quite far from the actual Q function. And so you can make that choice. But I guess our perspective is that you should decide on the estimand, first, from the science, and then say, now we're going to commit ourselves to figuring out how to do inference for it. So, it's an interesting question. I mean, this has come up in other forms. I think I even saw something in Q-learning where they did try to do this. I'm now trying to remember.
You could argue that if so here you assume ahead of time that you have like some pretty discriminatory choices, right? I do this or I do that, and they're binary, and hopefully they're gonna just very, very polarizing. But if two options, like let's say you don't know ahead of time, they actually have the same outcome, like your CDC person is not good at their job and it's pretty much the same as talking to a wall, then you won't see any difference. And in which case, rather than actually paying a lot to actually go for the max, you might just toss a coin and just say, I'm going to do half-half, which is what the softmax would actually encourage you to do. And right, that's what the softmax does. It says if there's very little difference between the two options, then I'm just going to toss a coin.
Yeah. So this is a this has been explored a bit, and I think in this case, you might be able to argue that if you could show that the softened thing was a lower bound, like if you got a lower bound by shrinking it inward, which I think maybe you could probably argue would be the case, then you could say, well, if that thing is close and it's better than business as usual, then I feel pretty good about it because right. And so I definitely hear what you're saying in that case. From the inference side, so in the inference side of these things, there's been the pushback would be that the inference for the softmax thing will probably not be very good for the estimand defined through the max thing because of this bias smoothness trade-off. Yeah, but I think it's a great point. I mean, I think you probably could smooth this out and then try to make an argument that it's a lower bound. You show that thing's better than business as usual, then you're already set. And then you would argue maybe that like if you couldn't detect it, then maybe it's not worth it anyway, because that just sort of suggests you're hanging around the boundary and yeah. So that's a great point. Yeah. Sorry. Okay. Let's see. I might skip some things here in the interest of time after our power outage, but the summary here and this is that we're going to estimate the optimal regime. The performance, we can't estimate the performance using the Q function because we're not assuming it's right. And so to kind of work from the bottom up here in great slide style, we're going to use the augmented inverse probability weighted estimator of the value. And the way that this is defined is for any beta. So this contains both the first stage and second stage coefficients for is indexing a Q function. You define this term delta of beta, which is 4 times y. So this is really, we're assuming half-half randomization here, times an indicator that the treatment was assigned in a way that's consistent with the Q functions indexed by these betas, plus a mean zero augmentation term to reduce variance. And so I won't go into the definition of this, but this is well documented in for example, CADIS 2006. But the idea is that the value under the Q function can be written as the expectation of this delta term. Right. So for any Q function or any policy indexed by beta, so beta indexes a Q gives you the policy. So there's a one-to-one correspondence. Is the expectation of this function delta, and V hat is just the empirical expectation of this delta. And if you estimate beta and plug that in, then you get back the AIPW. Okay. So V hat with the estimated coefficients is the augmented inverse probability weighted estimator of the value of beta star, which is in fact the value of the sort of the best you can do in terms of these Q functions. So the point is that we have this sort of estimator that's consistent because we're using inverse probability weighting, whether or not the Q functions are correctly specified. And so that's what we're going to use for our sample size. Okay. So the idea here is to invert a test, which is a standard kind of approach to dealing with non-regular problems. And we're going to invert a projection test. And so the idea here is pretty straightforward. I think you first, we're going to define this, I don't know, this is a var sigma. I'm not sure. I don't know why I put a symbol on a slides that I couldn't pronounce, but let's say it's var sigma of beta, which is just the variance of this delta. And then we'll define Zn of beta. So here we're regarding beta as fixed as root n v hat of beta. So that's the value of the policy indexed by the Q function with parameters beta minus the true value function for that coefficient beta divided by the estimated variance. So that would be Pn in place of P here. So this thing is going to converge to normal. And the reason is that when these are fixed, this is just a central limit problem, central limit theorem problem, right? This is just an average. This is its expectation, scale up root n. For beta fixed, this is going to be standard normal. And the idea is if we knew what beta star was, we could just plug in beta star in place of beta and everything would be fine. The challenge is that we don't know what beta star is. And so the idea is you can first construct a confidence region for beta star, can then use the fact that this is normal for every single beta and then take a union over betas in the confidence interval for the true coefficients. And so this is the idea of a projection test. So what the idea is that you're going to take a 1 minus theta 1 confidence region for beta star. And then you are going to have a test that rejects when you take the inf over this confidence region of v hat of beta minus z1 minus theta. So this is the 1 minus theta quantile of a standard normal times your variance or your standard deviation estimate over root n when this thing is bigger than b0. And to see why this is a valid test, notice that if you knew the true coefficients, if you could put a beta star here, then you just have something that was asymptotically normal and you just took the normal quantile times the standard deviation divided by root n. You reject when it's big, right? And so the idea is that you reject only when the inf over this confidence region exceeds this, and so that makes it conservative, right? And because beta star belongs to this confidence region with probability 1 minus theta, the error of a test of this form is no more than the sum of the two errors. So there's one error, which is that this set contains beta star. Another error would be even if you had beta star, that this test would commit a type 1 error, and that would have probability theta 2. So the overall error is the sum of those two things, theta 1 and theta 2. If in fact the null were true, which is that the performance of the optimal is no better than business as usual. So this is the test. And so the nice thing about this is that it just composes nice sort of regularly behaved kind of quantities, and so that makes this the sort of this easier to work with. Okay, so this is an ugly looking slide, but let me just say what it is. This is just the power of the test. So it's the probability that test statistic rejects. And so all that's happened is a little bit of algebra has been done to kind of isolate important terms. So the first term here is this Z thing. This is this asymptotically normal quantity here. Okay. And the second term is something we're used to seeing in doing power calculation. It's, I'll say n sub n of beta, which is root n times the true value at beta minus standard of care. So this is like the effect size, right? So if this thing is, if we had a beta star here, this would be exactly the effect size. It'd be root n times the difference between the actual value and the null, right? And so if they're big, it gets scaled by root n, the power goes up. The challenge here is that there's a beta and not a beta star here, right? So we're taking inf, and the inf affects both parts. And this is bounded below by the inf if I take obviously the minimum of this with anything, but it's the minimum of this with the minimal clinical difference. And the reason that we do this is we're going to bootstrap the data. And when we bootstrap the data, obviously we'll be using the estimated data generating model and not the null, right? And so what you don't want is you don't want to ensure, let's say 80% power, no matter what the actual clinically meaningful effect size is. You want to do it so that you get 80% power at the minimal detectable effect size, and then it will be bigger if you happen to exceed that effect size. And so to do that, you replace this difference here with the minimum of that and this minimal detectable effect size eta. So you're replacing VQ beta minus B0 with eta and just putting that here. And that ensures that in fact, if the sort of truth of the matter is that you're much bigger than the standardized effect size, the power will still, if you calibrate this correctly, the power will still go to 1. Okay. So of course, looking at this, it's not surprising there's no closed form expression for the power. But the way that we do this now is we collect pilot data of size n0. And then we use bootstrap oversampling to estimate the power, and we solve for the sample size that attains nominal power. So this is a very sort of simple procedure. This is done a lot in clinical trials. Typically, N0 is quite small. So we have one trial with 25, one trial with 50. And you can show that if you bootstrap data, so if you're doing this oversampling bootstrap thing, so we're going to sample, let's say, n from N0, and we'll let P N0 N B be the bootstrap empirical distribution induced by sampling n from N0. And for any function, let's say Wn, which is a function of the truth and the sample distribution, we'll just add a superscript b to denote that same function of the sample distribution and the bootstrap. So we just, the bootstrap analog of this thing, right? Then the sort of bootstrap power is just solving for integral n such that the bootstrap analog of that expression for the power. So this is the bootstrap probability. This is that inf over the projection set. This is the bootstrap analog of the test statistic, that this thing is at least 1 minus gamma. So this is obviously very, computationally intensive. And so that's in sort of ad hoc, all right? So you wonder, like, can you provide any sort of performance guarantee? And it turns out that you can. And this horrific slide basically says that if you fix theta and we look at local alternatives to the standardized effect size, so eta sub n is the standardized effect size plus s over root n. So this thing is a local alternative to this sort of minimal detectable effect size that we care about. Then you can show that the limit is n0, that's the pilot, and n go to infinity, that the difference in power, so this is basically the power curve. So this is the bootstrap power curve. This is the true power curve. This thing goes to 0. So the point here is that the bootstrap power curve converges to the actual power curve over all compact sets is the take-home message. And then the, massive notation is just operationalizing that. But so this is the bootstrap power curve. This is the actual power curve. It converges uniformly to 0. Okay. And so one sort of interesting side note from this project is that a lot of these resampling procedures are used, but there wasn't a lot of formal evidence that they actually did the right thing. And so this provides a little bit of assurance that, in fact, you do actually get consistency. So this is over all possible sort of divergences to infinity, but generally you care about the case where n goes much faster than n0, and it holds in that case. Okay. All right, so just to summarize, we looked at a projection test and bootstrap oversampling. We showed you a consistent estimator of the power curve, which is going to give us our power criteria. You can do an analogous thing for the optimality criteria, which I didn't show. We did not assume a parametric model or a correctly specified model. It's obviously more complicated. The nuisance parameters are difficult to elicit, so instead we used either an interim pilot or historical data to seed our bootstrap. And then just in the last minute or two, I'll just go over some quick simulations. So the idea here is we're kind of trying to take the worst case. So we're taking these sort of non-standard cases where we expect sort of standard methods to perform poorly. Look at a model that's linear at the second stage, has normal errors. The Q functions are both correctly and incorrectly specified. We look at a pilot data set of size 50. So generally, the combined sample size of the pilot and what you need is much, much smaller than what you would use in 2 trials. We'll have a type 1 error of 0.05. Desired power is 90%. The probability of being near optimal will also set to be 90%, and we'll select sample sizes so that both those criteria hold, power and optimality. And we look at the parametric and non-parametric procedures, and we'll do that. We'll compare that with the sample size required to compare 2 fixed regimes using a t-test, and just to make it, sort of even to make the sample size even more of a difficult benchmark, we pick the 2 regimes that are farthest apart so the power is highest. Let delta be the difference between the mean outcome under the optimal regime and the best non-adaptive regime in sort of standard of care units, so that delta equals 0 is this case where there's absolutely no benefit to tailoring. Right, so it's this case where you've gone through all this exercise of estimating a rule, even though tailoring has no additional benefit over giving every person the same treatment. And we'll look at two methods for selecting sigma. So either it's known or it's estimated using an interim pilot of size 50. Okay, so here are the results. The top table is if the model is correctly specified, the bottom's misspecified. This is for the parametric model. And so what we see here is that these rows are different effect sizes in terms of how much benefit you get from tailoring. So it's increasing. And we also have the method for choosing sigma. And remember, these are supposed to be around 90%. And we see that at the worst case, where there's nothing going on, we do hit nominal levels, slightly under here. And then as the effect size increases, the power increases, which is what you'd expect. If it's misspecified, however, you get this mixed bag because you have no guarantees now, right? And so here it seems to be okay, but look down here. I mean, this is even though the effect size is big, the power is 77%. It's supposed to be 90. And what's happening here is you're converging to the wrong place. And so it's going to get worse and worse. So the bigger you make this effect and the bigger you make the sample size, it's going to get even worse, right? Because you're converging to the wrong quantity. So the point here is it seems to be it can be sensitive to misspecification, which I think is an important warning. If we look at the actual required sample sizes, so this is fixed if you just did a simple comparison versus the expected sample size under this sort of procedure. The fixed one doesn't change, so that's why it's given as fixed. So you can see that even though we are sizing for this much more complicated comparison, it's not orders of magnitude bigger generally. And in fact, if personalizing gives you a huge benefit, you can in fact even sometimes require a smaller sample size, which is not surprising because you can always make it so that there's no difference between fixed treatments and that adapting gives you a huge benefit. But if we go to the misspecified case, then sort of all bets are off. You see that we can end up with very large sample sizes or small, but then we don't have enough power, right? And so this misspecification issue seems to be serious, or at least something you can't ignore. You need to do diagnostics. If we go to the non-parametric case, I wrote correct and incorrect. Just that's when the parametric's correct or the non-parametric's incorrect. There is no assumption of correctness here. The Q functions are misspecified regardless. And here we see that in the worst case, we are slightly underpowered. But the one thing that's going on here is that there are some cases where the bootstrap sample basically finds no difference, and so you can't proceed. You basically say there's no benefit to tailoring at all. And so if you sort of put this together with this, you end up with sort of the right power. But one of the issues is that if tailoring appears to be worse for patients, there's no extrapolation that's going to ever make it look better, right? And so you can see that when there's nothing going on in a sample size of 50, then 16% of the time, in fact, we end up with this sort of null result, which says you can't get a sample size. And so that's why this is 72, because 16% of the time it's failing, right? But as the effect size gets bigger, we fail less and less, and the power gets to be close to what it should be, and then it's approaching 1. The same thing happens down here. This other class of models, again, here, about a quarter of the time, there is no benefit to tailoring, and so we do our interim pilot, and it basically says we can't compute a sample size at which you would ever have enough power, and so on those we fail. And so actually, if you take those out, the power is not so bad. And so it's not surprising that with the sample size of 50, you can come back and say there's not enough information here. Okay, so I think we're just about out of time. So maybe I'll skip over the sample size and just say we talked about sample size procedures for precision medicine and showed that at least it seems to be possible. They don't seem to be as conservative as people maybe feared they were. You can guarantee, frequentist operating characteristics across a range of different assumptions, going from strong parametric assumptions to non-parametric or just kind of moment type assumptions. We had to make some elicitation of information, which is standard in sample size procedures. So either through historical data or pilot data, asking clinicians for values related to variance, or by putting more structure in the model. And I think these are just first steps. There's a lot of open and interesting problems, and I'd be happy to talk about those. So I think with that, I will stop. Thanks.
Thanks, Eric.